Hello and welcome to another video. In this one we're starting our new unit on inductive and deductive reasoning. So in this lesson we're going to be looking at inductive reasoning. Before we actually get into this investigation here though, I just want to go over some terms that we should know related to some different number sets. So natural numbers, these are your natural counting numbers like you could count on your hand, 1, 2, 3, and so on. Whole numbers are natural numbers, but now it includes a 0. And then integers are the whole numbers, but also now it has the negatives going this way. Odd numbers, these ones should be a little easier, 1, 3, 5, and then also -1, -3, -5, and so on. Even numbers, 2, 4, 6, 8, and so on, and then the negatives of those. And then prime numbers, these are numbers where the only factors that can go into it are 1 and itself. So now that we've looked at that, let's go back to that investigation here. And it says, use a strategy to determine a pattern between the figure number and the number of congruent triangles in each figure. So we're going to try to figure out, if I'm given a certain figure number, I can figure out how many triangles are going to be in that figure. So first thing we're going to have to do is know how many triangles are in each. So we're going to count them up. So first one's got 1. Second one has 1, 2, 3, 4. The figure 3 has 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then I'm just going to write those over here. So figure 1, it had 1 triangle. Figure 2, we got 4. Figure 3 had 9. So we're going to try to come up with a pattern or some type of method to figure out when I get down to n, how many triangles I'm going to have in that. So if you want to try to figure out a way to go from 1 to 1, 2 to 4, and 3 to 9, I'll give you a sec to try to figure that out. So in all of these, going from one to the other, we can see the numbers getting larger. So in the first one, it went from 1 to 1, 2 to 4, and so on. So the way that we can go from this side to this side is we just square the number. So if our number is n, to get to the number of triangles, it's going to be n squared. So now that I know that pattern, I can use that to answer this question. So it says, how many triangles would be in figure 8? So if I know it's figure 8, all I got to do is square that, and that'll give me out how many triangles are in that figure. So 8 squared is going to give me 64. So there's 64 triangles in figure 8. The next thing it asks is determine a statement to describe the pattern. So we've kind of said it in words, but we want to actually write it out now. So to get the number of triangles here on this side, what we needed to do was we needed to take the n and square it. So we needed to take the figure number, right? That's what we had here, the figure. We had to take that and square it. So I'm just going to write that here. So the number of triangles is equal to taking the figure number and then squaring it. So at the bottom here now it says, in the investigation we developed a conjecture. So that word conjecture, we're going to see the definition for it. You might have heard of it before though. So we developed a conjecture about the number of triangles in each figure by observing patterns in figures. So we looked at a few of these, we noticed how it was going from one to the other, and then we came up with our own way of how we thought it was going to happen. Then it says you used inductive reasoning to develop your conjecture, and we're going to see the definition for that as well on the next page. So moving to the next page here, the definition for conjecture, it says, is an unproven conclusion based on evidence. So you could make the conjecture that maybe some sports team was going to win in the playoffs this year, and it was based off how they had been performing in other games. It can't be proven, right? It's actually going to have to happen for you to know, but it's a conclusion that you've come up with based off some evidence. Some other words for conclusion could be a generalization and also a educated guess. So those all mean the same thing. Looking at inductive reasoning, it says for that, it is a type of reasoning used to draw a general conclusion based on experience, observations, or patterns in specific examples. So you're basically looking at some specific examples or cases or scenarios, and then you are coming up with this conclusion from that. So you're going from something really specific, and then you're kind of making a generalization of what you think is going on. So you're going from specific to general. So an example of this could be maybe you've had some specific days where on certain days you wore maybe your blue pair of shoes, and every single day so far when you wore those blue shoes, it rained. So you could make a conclusion, if you wore your blue shoes, that day it's going to rain. So that was based off your experiences or your observations. You came up with a conclusion. It may not be correct, but you came up with it based off your own experience or observations. So in this first example here, it says make a conjecture about the product of two odd integers. So what we're going to do is we're going to do some examples where we take some odd integers and take their product. Remember, product, that means multiply. So let's maybe take, say, 3, and we're going to times that by 3, and we get 9. Okay, make sure you do a few of these. Don't just do one and then come up with a conjecture. So I could do, say, -5 times 7. When I do that, it'll give me -35. You could do another one. Maybe you're going to take 9, times that by 11, and we get 99. So I'm just taking odd integers, multiplying them, see what I get. So I could make some different conclusions about this. If you wanted to try to come up with one first, I'll give you a sec to try to think about one. So the one I came up with, it seems like whenever I multiply these odd integers, I get out another odd integer. So I'm going to make that conjecture. Let's just write that. So the product of two odd integers equals an odd integer. Now this conjecture that we just came up with, it is not proven. We have only came up with it based off some examples, but it is not yet proven. To prove that, we need a different type of reasoning, and we're going to look at that in the next lesson. That is called deductive reasoning. So moving to the next one here now, it says make a conjecture about the difference means subtract, between consecutive perfect squares. So difference means subtract, consecutive means one right after the other, and perfect squares, those are like 1, 4, 9, 16, 25, and so on. Those are your perfect squares, like 1 squared, 2 squared is 4, 3 squared is 9, okay, and so on. It then says, is it possible to make more than one conjecture? So we're going to try to come up with something first. Again, we're going to base it off some examples. So let's take some perfect squares and let's subtract them. So I'm going to take for the first one 4 and 1, and I'll subtract those. So I'm going to go 4 minus 1, and I get out 3. Then I'll take the next two, the 9 and the 4, so I'll go 9 and 4, subtract those, I get 5. Remember, they have to be consecutive, so I can't take like 1 and 9, that's skipping 1, that's not consecutive. Let's do another one, let's do the 16 and the 9, so when I subtract those, we get 7. And we'll even do the last one, 25, subtract 16, subtract those, you get 9. So if you want to try to come up with a guess or a conjecture about what we're getting out for an answer, you could do that now. So again, with this one, it seems like the values that we're getting out, they all seem to be odd. So we could make the conjecture that the difference between consecutive perfect squares is always an odd integer. So that's just kind of one conclusion or one conjecture you could come up with. It also asked us, is it possible to make more than one conjecture? So you could possibly come up with another conjecture. So if you want to try to think of something else, try to work with the numbers and see what you get. Just pause the video. So the one that I came up with, just working with some numbers and trying some things, is you could have this. So adding this square root, that's just what this stands for right here, SQRT, square root, of each number it actually gives out the same result. And I'll show you some examples. So we'll take the first one there where we had the 4 and the 1. So if I took the square root of 4 and I added the square root of 1, the square root of 4 is 2, and then the square root of 1 is 1, so 2 plus 1, I get 3. And that value there, that is exactly what we had before. Okay, I'll do another one here where we check it out. So we'll do square root of 9, and then add the one before it, square root of 4. Square root of 9 is 3, plus square root of 4 is a 2, and 3 plus 2, we get 5. And again, that one is the same as what we had when we subtracted them. Okay, so that's just kind of one other conjecture you could have. Maybe you came up with something different. As long as you can show it, that is fine. So moving from there, the next thing we're looking at here are properties of inductive reasoning. So it says for inductive reasoning, it does not always prove something to be true, right? Like the one example I said where every time you wore blue shoes and it rained that day, just because you keep wearing blue shoes and it happens to rain, that doesn't prove that that is true and that is always going to happen. There could exist a counterexample. So maybe one day you wear your blue shoes and it doesn't rain. Okay, that would prove that wearing those shoes does not make it rain. So all a counterexample is, it's an example that shows the conjecture to be false, and that would disprove the conjecture. Now for a counterexample, you only ever need one counterexample to prove something to be false. So as soon as you have one thing, you've disproven the conjecture. You don't need to provide another. You only need one thing to prove something wrong. And then the second point here about conjectures, it says more support for a conjecture strengthens the conjecture, but it does not prove it. So maybe you did 3 days with the blue shoes and it kept raining, and then you did 5 days, rained on all 5, 6 days, rained on all 6, but gaining more days and it raining does not prove that that is true. It just adds more data, which leads you to think that it's true, but it still might not be true. So looking at this next example here now, it says a student states the following. So they had 1 times 9, they got 9, 2 times 9, 18, and they worked their way up to 4 times 9, they got 36. And then what they did was they took those digits, so 1 and 8, they took those, they added them, and they got 9. Then they took the 2 and the 7, added those, they got 9. 36, 3 plus 6, added those, they got 9. So they made this conjecture. They said if a number is multiplied by 9, then the sum of the digits of the product is going to add up to 9. So we did this product, we got our digits, we added them together, it gave out 9. So that was their conjecture. Now it says, do you agree or disagree with this conjecture? So if you want to maybe try some examples and see if it still is true with some other ones, you could do that. So hopefully you tried playing around with the numbers. Maybe you found some more numbers that worked, but maybe you found one that didn't work and you disagree with their conjecture. So I'm going to say for this one, because I tried some numbers, I'm going to say that I disagree with this. So I found a counterexample where I took 9 and I times it by 11. Now 9 times 11 gives me 99. So taking those digits and adding those up, I'm going to have 9 plus 9, and when I add those, I get 18. So this answer that we just got, 18, that's not what they said it was going to add up to. They said it was going to add up to 9. So I found one counterexample, so that disproves their conjecture. So kind of the second part to this, it says, can you improve this conjecture? So could you somehow change their original conjecture so that it still is true no matter what? So what you could do is you could put a little restriction on it. So you could restrict the numbers that you're going to use, because you can see they used from 1 all the way up to 4, and this actually works all the way up to 9. So I'm going to restrict and only use the numbers from 1 to 9. So 1, 2, 3, 4, all the way up to 9. So if I restrict it to those numbers, then their conjecture, it would hold true. Lastly here for this one, we're going to do another conjecture that you could have for this. So what you could say is if you maybe kept adding the digits that you kept getting, like in this one we had 1 and 8 at the very end right here. So if I added those again, then I would have got 9. So you could maybe add on to this conjecture, if you continued to add the digits, you would get 9. So that was our last example. At the bottom here now, I'm just going to put up our textbook questions. So it's on page 22. Number 1, you're just doing those letters, A, B, D, F, and G. And just a quick note for some terms that you're going to need to know. It says there at the bottom, so you're going to need to know what a quadrilateral is and also what multiples of 3 are. So quadrilateral, all that is any shape that has 4 straight sides. So like a rectangle, a parallelogram, a square, a kite shape, anything with 4 straight sides. And then multiple of 3, you probably know that one, but that's like 3, 6, 9, 12, okay, and so on. Anything that could be divided by 3.